So this video will discuss trying to identify where a function has horizontal and vertical asymptotes by analyzing limits. We're going to refer back to this graph a little bit later on in the video. You see this graph has a vertical asymptote at x equals 4. Horizontal asymptote looks as if it's the x-axis. This graph has another unique characteristic that I've kind of added to the graph myself. There's actually a hole poked out of this graph at the x value of -2. So how do we figure out what exactly is going on with this graph if we don't have access to the graph, if we have to use limits to perform this analysis? So just some information that we'll need to use throughout this. X equals c is a vertical line, and it will be a vertical asymptote of a function f of x if two things happen. Your function is going to be undefined at the location of a vertical asymptote. More importantly, if you check the limit as you approach that location where your function's undefined from either the bigger and or the smaller side, if you are able to show that your graph is moving up off the coordinate plane to positive infinity or down off the coordinate plane to negative infinity, you've shown that that is the location of a vertical asymptote. So two things: where's the function undefined? Do I get a limit answer of positive infinity or negative infinity as I approach that x from either side? Technically, condition 1 doesn't need to be satisfied. It's such a rare circumstance to have a vertical asymptote at a location that does have a point on it for a function that I always tell my students that this is something that you're going to want to make sure you're identifying. Horizontal asymptotes, y equals c, that's a horizontal line, and it's going to be a horizontal asymptote of a function f of x if either or both of these limits are true. The limit as you approach infinity for your function is equal to that constant value c, and or the limit as you approach negative infinity for that function is equal to a constant value c. So basically what this means, if we go way over to the right edge of the graph, x approaching positive infinity, and the graph is leveling off at a certain y value, we have a horizontal asymptote at that y value. If we go way over to the left edge of the graph, right, x moving to negative infinity would push us way over to the left side of the coordinate plane. If our graph levels off at a specific y value, we have a horizontal asymptote at that y value. So here's the function that we're going to be trying to analyze, and you did see a graph of this function on that opening screen, so you should know a little bit about what the conclusion here is going to be. But how do we identify where this function has vertical and horizontal asymptotes? Before we go across this top line, let's look at this horizontal asymptote analysis that I did. So there's two limits that you check for horizontal asymptotes. They are always the same limits. What's happening way over on the right edge of the graph as x approaches infinity? What's happening way over on the left edge of the graph as x approaches negative infinity? Now, if you were to put infinity in place of all of these x's, what you would get is you would get infinity over infinity. That is an indeterminate form. Now, for those of you that are later on in your calculus course, you would be able to use L'Hopital's rule to get past that indeterminate form. Early in a calculus course, I'm talking like first unit of the course, you'd probably only know this trick that you've seen I've applied right here. I looked for the highest power of x from the denominator, which was x squared, and I divided everything in my rational function by x squared. I then simplified. So when I divide x by x squared, the x in the top is going to cancel with one of the x's in the bottom, and then I'm left with 1 over x squared in that position. No simplification happens here. The x squared and the x squared divide out to be a 1. This x is going to divide with one of the x's that's in the denominator, so that becomes a 2 over x, and then no simplification happens here. Putting infinity in place of this x, this x, this x, and this x gives us 4 fractions, 2 in the top, 2 in the bottom, that are all fixed values over infinity. A fixed value over infinity is going to trend towards 0. If I'm looking at 0 plus 0 over 1 minus 0 minus 0, that's 0 over 1. That is 0. This top line right here confirms that we do have a horizontal asymptote at y equals 0, at least on the right edge of the graph. Now, when you are dealing with a rational function, and a rational function is simply a polynomial over a polynomial, This same strategy works as you approach negative infinity. So for rational functions, these limits are going to be symmetric. Now, don't assume that every limit as you approach infinity for a function is going to be the same as every limit as you approach negative infinity for that function. If you're dealing with exponential functions, you might not have the asymptote on both sides of the graph. If there's some sort of absolute value at play within your function, the asymptote might be different on the two sides of the graph. So you do want to definitely analyze both of these limits. But in the case of a rational function, polynomial over polynomial, same trick works. Like this fraction right here, 1 over negative infinity is now a negative fraction, but 1 over negative infinity is still a fractional value that's really close to 0. So I am going to get the same conclusion as I approach negative infinity. This horizontal asymptote of y equals 0 is symmetric on both sides of my graph. Now for the vertical asymptote analysis, we want to first ask the question, where is the function undefined? This function is going to be undefined when the denominator takes on a value of 0. So I'm setting the denominator equal to 0, solving that equation by factoring. This factor is equal to 0 when x is 4. This factor is equal to 0 when x is negative 2. So there are two locations that I have to analyze as being potential spots where I have a vertical asymptote. We're going to determine whether or not we in fact have a vertical asymptote at either or both of these by checking limits. So I'm checking the limit as x approaches negative 2. When I put negative 2 in place of the x that's here, and in place of both of the x's that are in that denominator, what I end up with is I end up with 0 over 0. Now 0 over 0 is not a value that tells you the conclusion for your limit. 0 over 0 is an indeterminate form. And that's a signal for us early in our calculus course to try to do some algebra and get something to cancel. So you do see I have the factored form of the denominator here. And if I cancel the x plus 2 factor with the x plus 2 factor from the denominator, what I end up with is I end up with 1 over x minus 4. You see that work is repeated again down here. And if I put negative 2 in place of the only x that's left, I'm looking at 1 over negative 2 minus 4. That's 1 over negative 6, negative 1/6. This answer does not indicate that I'm moving up off the coordinate plane or down off the coordinate plane on either side of negative 2. It indicates that I'm approaching a removable discontinuity, which is a hole poked out of the graph at negative 2, comma negative 1/6. Now if I click back to that graph, you can definitely see that that is the case. Now I use Desmos to graph this. Desmos isn't going to really have the capability of showing us that hole poked out of the graph, neither would a handheld calculator. So it's kind of a unique situation. You've probably talked about this in other problems within your calculus course, but there is a hole poked out of this graph at the x of negative 2 and the y of negative 1/6. Now, x equals 4 is a vertical asymptote. What confirms that? Well, if I consider putting 4 in place of this x and both of these x's, I end up with 6 over 0. 6 over 0 is undefined, and it's undefined because it's an infinite answer. It's either positive infinity or negative infinity. The way you're going to establish which it is by carefully analyzing one-sided limits. So what's going on the bigger side of 4? What's going on the smaller side of 4? Now, I am dealing with this version of the function. There is a difference between what we have here initially and what we have here on the right side of the screen. This version of the fraction is only undefined at 4, whereas this version of the fraction is undefined at both negative 2 and 4. The only difference between the graph of what we have here and the graph of what we have here, the graph of 1 over x minus 4, it would be this graph without the hole poked out. But when I'm checking limits, I am allowed to simplify within that process. So you can check these limits with the original version of the function. I think it's a little nicer to check it with the slightly modified version. There's just a little less going on. There are fewer x's in this version of the function than what's slightly different issued as the original version of the function. So I'm checking the limit on the bigger side of 4. When I put a number slightly bigger than 4 here, and I subtract 4 from it, I do end up really close to 0, but I'm slightly positive. A positive divided by a positive is positive infinity. When I check the limit on the other side of 4, at a value like 3.9, slightly smaller than 4, 3.9 minus 4 gets me really close to 0, but does take me a little bit to the negative side of 0. A positive divided by a negative is a negative answer. Technically, the limit as we approach 4 in general does not exist. The one-sided limits don't have the same value, but we have confirmed that our graph is moving up off the coordinate plane on one side and down off the coordinate plane on the other side of 4, and that does tell us that x equals 4 is a vertical asymptote. And if we go back and check out that graph one last time to wrap this discussion up, this is the bigger side of 4. If I get on the graph and I move toward 4, yeah, my y value is definitely trending toward positive infinity. This is the smaller side of 4. If I go on the graph and move toward 4 along this graph on the smaller side, I'm going toward negative infinity.